Alright, what's up mga Chimek? So we're down to the last few gas laws. So last time we've talked about the first two gas laws, the Boyle's law and the Charles law. So just a quick recap. So to understand the behavior of the gas, again we have to remember the properties of the gases. Specifically, that gas are compressible, that gas randomly moves, no, inside the container, and if you can remember, no, the kinetic molecular theory, that as we increase the temperature they move faster. And so to proceed with the different gas law, let's take a look at the first two gas law, the Boyle's law and the Charles's law. Again, some book would just say Charles' law. Different school, different pronouncement, right? So Boyle's law states that the pressure and volume of a certain gas is directly proportional, no, at constant temperature. And we are also assuming that the number of moles is constant. So at constant N, no, or at constant number of gas. For the Charles law, it states that the pressure, the volume rather, the volume and temperature are directly proportional. So meaning, as we increase the temperature, the volume increases as well. And as we decrease the temperature, the volume decreases. This is at constant pressure. So please do remember these first two law. We have rewritten these laws so that we can use them to solve the initial and final volume and temperature and so on and so forth by stating that PV, P1 V1 is equals to P2 V2. And for the Charles law, it's V1 T1 is equals to P2 V2. Then, if one is missing, we can simply manipulate the equation to fill out what is needed, no, or to find what is required. So these are your first two laws. No? Again, si Boyle's law, though he was not the one who discovered it, it was named after him, but we still need to acknowledge, no, Henry Power. It was Henry Power who made the discovery, who crafted the evidences for the start, no, of the gas law, specifically the Boyle's law. That's what we call it right now. For the third law, we have the scientist by the name Louis Gay-Lussac, no? John Louis or Joseph Louis Gay-Lussac. It's a one name, no. Some students would often ask, "Sir, dalawang tao ba si Gay at si Lussac?" So it's just one name, no? It's one person rather. So Gay-Lussac's law. So he noticed the relationship of pressure and temperature just simply by looking at Boyle's law and Charles' law. Now, si Boyle's law, kino-compare niya si pressure and volume, while si Charles' law is comparing the volume and temperature. So, Gay-Lussac simply realized that maybe there's a relationship between the pressure and the temperature itself. Since pressure is related to the volume and volume is related to temperature with an inverse proportionality here and a direct proportionality here, he said that pressure and temperature are directly proportional. So, how did he say so? Say for instance, in the top of the mountain, if you've been into Isarog, now what is the temperature in Isarog? Is it high or is it low? You sometimes feel cold on the top of the mountain, therefore the temperature there is low. No? And sometimes, if you don't realize it, you find trouble in breathing because the pressure is also low. No, medyo mahirap huminga sa taas ng bundok kasi manipis ang hangin, no? And the pressure is very low. Even when you ride a plane no, mafe-feel yan sa tenga nyo. And that's the reason why athletes, especially, malimbawa, si Manny Pacquiao, he loved training, no, in the top of the mountain. So, magja-jogging siya doon para, yan, medyo ma-strengthen yung cardio niya, stamina niya, etc., etc. So, he realized, no, Gay-Lussac realized that the pressure and temperature are directly proportional, meaning as we increase the temperature, the pressure increases. And this is true to the examples we have already given a while ago. Say for instance, the can, no, the aerosol cans. When we increase the temperature in the aerosol cans, of course, the pressure of the gas na inside, it's increasing to the point that it would explode if we continuously increase the temperature. So this is the Gay-Lussac's law, where the pressure and temperature are directly proportional. Some would use this one, no? It's equals to a constant. And to be able to use this specific equation, we can simply write this as P1 T1 is equals to P2 T2. Our initial pressure, temperature, and final pressure and temperature. And of course, this is at constant, what do you think? At constant volume. Alright, at a constant volume, when we increase the temperature, the pressure would increase. So let's have an example, no? Again, knowledge has no value until we put it into practice. So my table is moving. Okay. Let's have an example problem. So say for instance, at a certain factory, no, which is 20 degrees Celsius, a tank storage has an initial pressure of 1.2 atm. So I will no longer write the problem. 1.2 atm. And then suddenly, the temperature inside the room increased from 20 degrees Celsius to 30 degrees Celsius. What would be the final pressure of the storage can? So we are looking for the P2. If you find trouble understanding in this video, I have uploaded already a handout, no, with examples and problem sets there, no, or example problems that you can try and you can you can check. Now, since we have the given, we will try to manipulate the equation in order to solve what is needed. So let me remove first our initial equation here so that I can make it a bit smaller. So that's P1 T1 equals to P2 over T2. So that would be P1 over T1 is equals to P2 over T2. I am looking for P2, so I need to multiply both sides by T1 T2. So T1 T2, so that the denominator would cancel out. T1 T2, cancel T1, cancel T2. That would give me P1 T2 is equals to P2 T1. And then I divide both sides by T1 so that I'll be left with P2. Cancel. That would give me P2 is equals to P1 T2 over T1. Alright? And we simply input the values needed. But, we forgot something, no? Before we input the value, again, for the gas laws, we use Kelvin, not Celsius. So remember the conversion unit. That would be degrees Celsius plus 273 to get our Kelvin. So 20 plus 273, that would be, dito ko na lang ilagay, 293 Kelvin. 30 plus 273, that would be 303 Kelvin. Alright, so this is my T1, and this is my T2. Now I can input them. P1 is 1.2 atm, and then my T2 is 303 Kelvin. Make sure to always write the units involved, and T1 is 293 Kelvin. Alright, so cancel the unit. We'll be left with atm. That's what we are looking for, P2. So let's put that into calculator. Sige. 1.2 times 303 divided by 293, that would be 1.24. That would be 1.24 atm. 1.24 atm. Now, not a significant increase because the temperature only rose 10 degrees Celsius. So, but nonetheless, let's check. We increased the temperature, therefore the pressure inside increased as well. Now, if it's in kilopascal, it would be very significant in terms of numeric value. So that would be 1.24 atm from 1.2 atm. Alright, there you have it, ladies and gentlemen, the Gay-Lussac law. So, please try another problem on your own.